Thank you, Tuka. And so first, I'd like to welcome you all to this 41st Stochastic Processes and their Application Conference. The SPA conference are among the most prominent conferences organized by the Bernoulli Society, and also is regarded as one of the most important international conferences on the theory and applications of stochastic processes. They are held every year, except in the fourth year, that is replaced by the World Congress in Probability and Statistics, jointly organized by the Bernoulli Society and also IMS. The last two SPA conferences were held in Moscow and also in Gothenburg. On behalf of the Bernoulli Society and also as the chair for the committee of the conference on stochastic processes, and I'd like to thank the scientific program committee chaired by Robin Pimentel and also the local organizing committee chaired by Tuka Ofgen and Greg Lawler for organizing, for their excellent work in organizing this conference, as well as the staff members and the students Tuka mentioned. And I'm sure that this will be a great event. Now, next year, it will be the World Congress year. So the World Congress in Probability and Statistics will be held in Seoul, Korea, from August 17 to 21st. I'd like to also take this opportunity to mention a new initiative by Bernoulli Society for recognizing research excellence by new researchers. The three young researchers are awarded for the 2020 Bernoulli Society New Researcher Awards in probability. They are Li Cheng Cai from Columbia University, Nina Holden from ETH Zurich, and also Xin Shen from Columbia University. At the World Congress next year in Seoul, they will give talks on their work in an invited section. Again, I'd like to thank you all for coming to this the 41st SPA conference, and I hope that you all will have a great time in the conference and also in Evanston. So now let's turn to the scientific part of the conference. And it's my great pleasure to introduce the first speaker for this conference, Jeremy Quastel. He will give the double lecture. Jeremy is a native of Canada. He got a bachelor degree from McGill University and a PhD from Courant Institute of New York University under the direction of S.R.S. Vladan. And after that, he did a postdoc at MSRI at Berkeley. And then after taught at UC Davis, he moved to Toronto University, where he's now as a chair, also professor, in 1998. Jeremy's research is mainly in large-scale behavior of interacting particle systems and SPDEs, recently concentrating on the KPZ universality class, and he has made many important contributions in these areas. Jeremy has received many recognitions, among them a Sloan Fellow from 96 to 98. He is an invited speaker at ICM 2010, and also a plenary speaker at the International Congress of Mathematical Physics in 2012. And he's a fellow of the Royal Society of Canada. Double lecture is generously supported by the Illinois Journal of Mathematics, and the speaker is selected by the scientific committee of the SPA conference. And this year it is held, it's chaired by Robin Pimentel. Jeremy is selected to deliver this double lecture for his outstanding work at the intersection of interacting particle systems and partial differential equations, and in particular for his work on a number of models in the KPZ universality class. So let's welcome Jeremy to give this double lecture. And I also have a placard from the president of the Plenary Society for Jeremy.
Oh, thanks. I get a plaque.
Yeah. You just take a photo.
Okay. Can you hear me? Yeah. So thanks a lot. It's a big honor, of course, and I hope Doob would approve of what I'm going to say. You know, Doob, of course, made a lot of contributions to the connection between probability and mostly linear PDE, and what we're doing now is connecting probability to nonlinear PDE, and there's some serious surprises. Okay, so I'm going to talk about the KPZ fixed point. KPZ is Carter-Parisi-Zhang, which is this story of growing interfaces. Strangely, in probability, there's another thing called KPZ in SLE, which is at least not directly related to what I'm talking about. Okay, so let's start. This picture, which I found on Cardar's webpage, tells the whole story. So we have some non-trivial topography here, starting out, this mountain and a tree and a car. And there's a one-dimensional snowstorm, two-dimensional snowstorm. So the snow's falling down, and it collects on top in layers. And what we are interested is the fluctuation of this interface. We'd like to know maybe its distribution, or maybe more interesting, we'd like to have an equation for it. So the problem for the hour is, what is the equation for random interface growth? Okay, so here's a movie of that where black snow is falling. It's called ballistic aggregation. If anyone doesn't know the model, particles are falling independently at every site from the sky. And they grow in stacks, but they also stick to the side. So the growth is outward instead of just up. Okay? So I'll just say it again. At every site of a one-dimensional lattice, there's a Poisson process of particles pouring down. And they either drop on top of the particle beside it, or they stick to the particle at the next site when they fall down. And that's why you see these outward growth and these diagonal things, which we want to understand. And of course, again, the question is, what would be the fluctuations of this boundary? So we want to write an equation for random interface growth. How would we do that? Well, we could try to write a stochastic partial differential equation for the height function. You could define a height function in the previous two things I showed you. A function hxt, which is the height of the thing at position x at time t. It would be some sort of stochastic partial differential equation. Or maybe we could compute something else. Maybe we'd be interested in, given the initial height function, like that non-trivial topography I showed you in the first slide, at some time t later, you'd want to know what the height was at, say, some finite m different points. Okay? If we knew that, you know that we know everything, because this thing should have the Markov property, and these finite dimensional distributions should therefore determine the Markov transition probabilities, just like the finite dimensional distributions of Brownian motion determine what a Brownian motion is. So either you could write an equation, or maybe you'd get these transition probabilities. Now, in finite dimensions, when you write stochastic differential equations, you learn that there's a recipe to go from the stochastic differential equation to equations for the transition probabilities. So if you have a stochastic differential equation, you write a second order linear elliptic PDE for the transition probabilities, the forward or the backward equation. But that kind of thing is missing in stochastic PDE. there's no obvious way in the non-trivial examples to go from the equation you have to the equations for the transition probabilities. That's one of our main problems. The other problem is we'd like a canonical equation for random growth. And what do I mean by canonical? Well, in particular, I want it to be scaling invariant. So we'll get to that in a minute. Okay, so I'll show you some examples. You may think the previous thing is contrived. Does anyone know what this is? That's a coffee stain being formed. If you're interested, there's a whole NPR has a whole site about this.
What's the size of a particle here?
There's the size of coffee when you grind it. The only thing is, it turns out you have to grind it very carefully for this to work. If you grind it in long oblongs, then it's not in this same universality class. That's the result of the paper, which is reported on NPR.
Is T the same universality class?
No.
Well, I knew the answer.
If you're from Canada like me, you've seen this all the time. The funny thing is, you see it in May. Anyway, okay. Okay, so this is a real thing. We're not dealing with some contrived thing. Okay. There's also models where it's not just a growing height function, but it grows out. So this is the most basic model of all. This is the Eden model. And the way the Eden model works is it just, it's a growing set on Z2, where you just add a site chosen at random from the boundary each time. Okay, so at each time step, there's a boundary. There's the collection of sites which are nearest neighbor to the set that exists, and then you just choose a site at random each time. The claim is it stopped. The claim is that after a long time, this thing has some shape. That's known. The shape's not a disk. Though, of course, you could make some model which was built to to make it be a disk, which is in the same universality class. But that doesn't matter. What we're interested in is what the actual fluctuations of the boundary look like, and therefore it doesn't matter if it's a disk. And in principle, what's supposed to happen is that if you look out here, if you look, say, in this direction, this interface is supposed to be growing the same way that the one-dimensional growing heights did. Okay? By the way, all the models that I'm talking about now, all these problems are completely open. And if you think that one was artificial, this is a bacterial colony growing. And you can see that the mechanism is basically the same as the Eden model. Okay. It's also supposed to govern forest fires, flame fronts. It's always supposed to be the same thing. Okay. Now, the question is how you'd make a model for something like this. So the first type of model you would perhaps try to make is a reaction diffusion equation. There's basically two states in such, is it working? Oh. There's two states in such a system. There's a metastable state, which is the unburned stuff, and then the stable state, which is the burned stuff. And what you've got is an interface of the stable invading the metastable state. There should be a coupling, which is this Laplacian, which keeps things together, and then you have a logistic growth. So you see it's dropping from the metastable to the stable with some noise. Okay. And then if you look at the region which is in the stable state, it's supposed to be growing according to these dynamics. Okay, so that's an equation for random interface growth. I hope it's clear. I hope you guys ask questions. We got lots of time. We started 5 minutes early, so there's 5 minutes for people to interrupt me with questions.
I thought that forest fires are different KPZ, Knižnik-Filipov-Malotchikov, but it also has dimension for thirds, so it's difficult to check.
Yeah, so many of the models I showed you earlier in pictures, it's actually controversial what class they're really in. And it kind of depends on exactly how you set it up. So it sort of...
set up forest fires.
No, you, you do set up forest fires. You set up, as Donald Trump said, if you sweep under the thing carefully, then you set up a different situation. If it's burning incredibly quickly, then the equation should actually be different than if it's sort of smoldering through. Okay? And so this sort of smoldering fronts are supposed to be this KPZ class. I'll leave you to decide what's in the other one. Okay, and same with bacterial colonies. You can actually see if you go look at pictures of bacterial colonies, you could tell which ones are in this class and which ones aren't. It matters exactly what's going on. Okay, but what we're talking about is supposed to be an incredibly general phenomenon of a stable phase invading an unstable phase, okay, or a metastable phase. Okay. Now the problem with an equation like this, you can write an equation like this. I just wrote it. But what are you going to do with it? It's not terribly clear how to analyze this thing. You might be able to show that the shape of the growing thing, there was some asymptotic shape, but you'd probably get no farther than that. The other problem is it has no scaling invariance particularly, and the noise, you said, well, it's uncorrelated noise. But what uncorrelated noise? You can't put a scaling invariant uncorrelated noise here, which would be something like white noise. So you've got an equation which is terribly uncanonical, with which you can't do very much. You can't prove anything. So Carter-Parisi-Zhang's contribution was to propose the following equation. And of course, there's a simplification. The simplification now is that there's actually a height function. Okay? That's not there in the earlier model. And of course, just the existence of a height function is already a big simplification, physical simplification. So the height function is supposed to evolve according to three basic mechanisms. Sorry about that thing. Okay. There's three basic mechanisms. The first, I would say, is this space-time white noise, which is forcing the system. The second is a relaxation term, which keeps the thing being an interface instead of it just having no connection from site to site. And then there's the most important term, which is this lateral growth mechanism. You see, in a system like this, if it's physically right, it shouldn't really know which way is up. It's just growing. So it grows out. And if you look at the vertical component of the growth, it's clearly a nonlinear function of the slope. Just look at the picture. The vertical component here is very different from the vertical component here. So you just put a nonlinear function here. And well, the physicists know that there's only one nonlinear function. It's a square. It's a little bit better than that. If you take a general nonlinear function, you could say, well, I'm going to expand it in a series. And then the first term, so you would have f of dhx. And the first term would be f of 0. And you can just remove that by a shift. Plus f prime of 0 dh dx. You can just remove that by a lateral shift. And then the first thing you discover, which you can't remove by simple things, is that. So you just leave that, and that's your equation. So that's how the physicists got this equation. Okay. Now, one thing about the KPZ equation which we know is that Brownian motions are invariant. So if you start this KPZ with a Brownian motion, so a Brownian motion here means a two-sided Brownian motion on R. And then you let it run. Then at a later time you stop it and look, what you'll see is a new Brownian motion. It's obviously not the same Brownian motion you started with, and it's very non-trivially correlated with the original Brownian motion. But if you just freeze it and just look there, it's a new Brownian motion. Also, if you start with anything, any smooth function, and snap your fingers, at any positive time, if you zoom in, it will locally look like the same Brownian motion. Okay? So the problem with the KPZ equation is that if you take a Brownian motion and you take its derivative, well, it has a distributional derivative, which is white noise. Distributions are fine as long as you don't try to square them. So the equation as written doesn't make any sense. Okay. Martin proved it's well posed. Of course, you have to subtract some infinity here. That's it. That's all I want to say about that. We're after something different, something much bigger. We want to know what this thing looks like on a huge scale, large space-time scales. The problem with the KPZ equation as a canonical equation for random growth, which is what the physicists say it is that it is not scaling invariant. If you look, the nonlinear term scales completely different than these terms. And so there's no scaling which takes the KPZ equation into itself. So it's not scaling invariant. So it is not a canonical equation for random growth. We're really looking for a canonical equation in the sense of the heat equation, which has diffusive scaling, or the wave equation, which has Euler scaling. Those equations are the canonical equations of mathematical physics, and they have this scaling invariance, and this one does not. Okay. So we're going to try to probe huge scales. And so one thing you've already seen with your eye as you watch the movie is that this thing is growing at essentially at some rate ct, where c is some non-trivial constant. I don't want to say what it is. It doesn't matter. These c's, the growth rates of such things, are terribly non-universal and depend on all sorts of intricate things about the model. Okay, but here's the interesting stuff. On top of this ct, the fluctuations turn out to be of size t to the 1/3. It's a very strange scaling. And they have a lateral size, which means the scale on which you see correlations of t to the 2/3. And this is the interesting stuff. Okay? Another way to say this is just a repeat of exactly the same thing, is that if you let epsilon be a small parameter, which is the relation of micro to macro world, so epsilon goes to 0, meaning you're zooming out, this is the scale on which you're supposed to see interesting things. So epsilon you should think of as the size of your lattice. And now this t to the 1/3 means you should rescale down by epsilon 1/2, and epsilon to the -3/2 is the time scale you want to look at. And if you do this, of course, this ct becomes enormous. Well, it becomes c epsilon -1t. So I'll call that c sub epsilon. So you just subtract it. Because you didn't care. If you want to see this front, you're going to zoom out. Of course, the front's going to go flying up in that scale. You just subtract it in order to see these interesting fluctuations at the front. So I hope everyone can see that this picture and this scaling just mean the same thing. So universally in these models, you're supposed to be doing this scaling to the height function and see something interesting. And the somethings you see are very interesting. You see things like random matrix distributions, which we're coming to. The distributions are extremely non-trivial in the limit. Okay. So the grand picture is that all these KPZ class models lie in a universe of models. This is not a well-defined thing. It's a huge, enormous dimensional space of models. Many of them Markov processes. Presumably, all the ones I showed you pictures of are models in this space. In this space, there exist two fixed points. There's a Gaussian fixed point, which in physics is called Edwards-Wilkinson, and there's this extremely non-trivial KPZ fixed point, which is the universal Markov process which governs all the non-trivial fluctuations you see in the limit I just described. These 2 points have 2 very, very different scalings. So, as we just saw, this thing, this is called 1, 2, 3 scaling. 1, 2, 3. In that scaling, every model in this class is supposed to be sucked into this KPZ fixed point. On the other hand, the Gaussian fixed point has what's called 1, 2, 4 scaling, and there's a mini universality where under this scaling, models which are specially tuned so they lie in this plane will be sucked into this Gaussian fixed point. Okay, so that's the general picture. I'm going to leave it up. You're supposed to think of this picture in analogy to a picture you know very, very well, which is the central limit theorem. So the universality of the Gaussian fixed point is because it is the measure on R which is invariant under the transformation of putting 2 of them together and renormalizing. Putting 2 independent random variables together and renormalizing. So there's a universe of distributions in 1 dimension, and under this map, everything is getting sucked into the Gaussian fixed point. Of course, the picture is a little more complicated. There's some which don't have variance, and they're getting sucked into Cauchy fixed points and things like that. But this is the general picture, and you're supposed to understand this picture in the same way as a huge version of that picture. Okay. The 2 fixed points have very, very different invariances. So, as you'll see a little bit later, the KPZ fixed point is invariant under the height goes to minus the height and t goes to minus t. You have to do both of them together for it to be invariant. Okay, that's called skew time reversal invariance. Whereas the Gaussian fixed point is invariant under h goes to minus h or t goes to minus t. It looks the same backwards as forwards. Okay. If we take one of our models, like noisy reaction diffusion equations, the story is supposed to be that if we looked at the front, and there the front is even hard to define, if you did this rescaling, you would be sucked into this KPZ fixed point. Weird. Oh, okay. Perhaps the most famous example is if you took the Ising model and you put on Glauber dynamics, and you were in a situation where you had a magnetic field, then one of the 2 phases in the Ising model is going to be more stable than the other. One's going to be stable and one's going to be metastable. And you'll have a blob, and it'll grow. And the fluctuation of the boundary under this rescaling should, in principle, converge to this KPZ fixed point. On the other hand, if you don't have any magnetic field, so imagine you had the Ising model. There's no magnetic field, so neither phase is preferred, and now you set it up with pluses on the bottom and minuses on the top. Then the boundary will just sort of fluctuate back and forth. There's no preferred direction. And so what you'll see is under this scaling, this thing should converge to this Gaussian fixed point. So it lives in this mini universality class because you've set the special value of the magnetization to 0. Okay. Now where's KPZ in this picture? The KPZ equation. So here's the KPZ equation with the parameter lambda, which is what you would call the coupling constant. Under strong coupling, this thing is supposed to get sucked into the KPZ fixed point. And as lambda goes to 0, it goes to this Gaussian fixed point. So now you know what the Gaussian fixed point is. The Gaussian fixed point is just this thing with lambda equals 0, which some people call the stochastic heat equation, and I call the infinite dimensional Ornstein-Uhlenbeck process. Physicists call that the Edwards-Wilkinson model. Okay, fine. So lambda is a parameter, and the KPZ equation is a heteroclinic orbit connecting this Gaussian fixed point to the KPZ fixed point as lambda increases, the KPZ fixed point being the strong coupling fixed point of the KPZ universality class. So this is a picture. And the only problem with this picture, it's a nice picture, except it's not so hard to prove things down here, but it was very hard to prove anything up here because nobody knew what the KPZ fixed point is. So for the rest of the talk, I'm going to tell you what it is. Yeah, so sorry, just a sec. So the only problem is the only way to find out what the KPZ fixed point is, because you don't have an equation, is to actually simply solve a model in the universality class and take the limit. And that model's TASEP. Okay. So TASEP, I'll tell you what it is now. TASEP is a Markov process on height functions, which have the special property that they're simple random walk paths. So the height function either goes up at each, this is a function over the integers, which I've drawn with little bars. So it either goes up one each time or down. So h of x plus 1 minus h of x is either plus or minus 1. That's called a simple random walk path. And this is a Markov process on the space of simple random walk paths. The simple random walk path can also be encoded with particles. Whenever it goes up, you put a particle, and when it goes down, you put no particle. And I hope everybody can see that the particle picture and the height picture is more or less equivalent. In fact, it's equivalent up to a single height at one point. But we don't care about such things because we're always subtracting CT anyways, okay? Okay. The dynamics is as follows. A little peak jumps to a valley at rate 1. And this happens independently at every one of the peaks. So at every site there's a clock, rings at +1 times, rate 1. And when the clock rings, if there's a peak at that site, it jumps to a valley. So just watch, there's a peak, it jumped to a valley. Now, of course, when the peak jumps to the valley, it's the same thing as a particle jumping to the right. And they all jump as long as there's nobody in the way. If there's somebody in the way, they're not allowed to jump, and they just wait for the clock to ring again and hope there's no one in the way next time. Okay, so here they are jumping. They jump, they jump. Okay? I hope everyone gets this is called TASEP. Totally asymmetric simple exclusion process. Okay. Now you may wonder, I said this is a special discretization of KPZ, and that's not obvious. But if you look, what's the rate of change of the height function? I want to write a stochastic equation for the rate of change of the height function. Well, it's just dh equals minus 2 indicator function that I had a peak, dt, plus some random junk, right? Does everyone see that? The rate of jumping down is just, well, minus 2 is because you jump minus 2, right? And you jump if there's a peak at that point, okay? But the world of discrete things is very strange. And if you do a little calculation, you can check for yourself that this function is exactly equal to the negative gradient of h, positive gradient of h, minus 1 plus the discrete Laplacian of h. The negative gradient being h of x minus h of x minus 1. The plus gradient being h of x plus 1 minus h of x. Okay? And I don't know if anyone did it in their head as fast as that, but I promise you, this is an exact relation. And now I hope everybody can see that this thing's a discretization of KPZ. So dh is just this And the only thing is, what's this -1 doing in there? Well, the -1, because all these things have these height shifts which you can't quite tell where things are, right? That can just be removed by a simple transformation. And those things are terribly non-universal. Does that make sense? Now you can also think for a second, well, if it's a discretization of this KPZ equation, maybe I could rescale it and it would converge to the KPZ equation. But that is not true. So this thing sort of lies in the space laterally to the KPZ equation. And you can't rescale it to get KPZ, because if you could, KPZ would have to be invariant under that rescaling. Okay? On the other hand, you can build out of this a model which will rescale to the KPZ equation. Instead of just having jumps down, you could have jumps down and jumps up. Okay? Well, I can just run the movie backwards. Yeah, the model now the jump up. Okay. All right. So if you have them jump down and jump up at the same rate, then it's just like in the dynamic easing model when you're out of magnetic field, and the interface between the two things just fluctuates back and forth. And now, under the 1, 2, 4 scaling, you're going to be sucked into the Edwards-Wilkinson, the Gaussian universality class. So what you do is you make the rate of jumping up very close to the rate of jumping down. And that's like making the nonlinearity small. And it turns out you should make the size of that epsilon 1/2. And so if the rate of jumping down is 1/2 greater than the rate of jumping up, and you do the 1, 2, 4 rescaling, the thing will kind of stay close to this manifold of the Edwards-Wilkinson and then get sucked into the KPZ equation itself. And that's the weak universality of the KPZ equation. And that's something one can prove, especially using the new methods of things like regularity structures. So these new SPD methods are very, very good for proving that. But they all stop at some finite time. None of those things can get you anywhere near this KPZ fixed point. Okay, so here's a picture of TASEP running down. That's what it looks like. Now we get to the interesting stuff. In the early 2000s, a number of people succeeded in computing the distributions of TASEP, for example, at one height at a later time, but only for very, very particular initial data. So for example, here the initial data is this.
Can I ask you a question? Are these things related to the convex envelope of Brownian motion, two-sided, or something like that?
I couldn't hear the one word. Are they related to what?
Yes. Are these things related to the convex envelopes of stochastic processes, two-sided Brownian motion, random walk? It seems that there could be relation.
So the question is whether there's a relation to the convex envelope of Brownian motions. And I think that's just because of the picture where it looks a little bit like some sort of convex envelope of a Brownian motion. But the answer is, I don't think in the way you're thinking, though there is some relation, which I could show you after. Yeah.
Or shifted Brownian motion by
Yeah.
linear.
So there is some relation, but it's not as simple as this. Okay. Yeah. All right. So so in this special initial data called wedge initial data, because well, it looks like a wedge. Here, I mean, this is literally the function you're starting with, this upside down v. Or you can think I'm starting with all particles to the left of the origin and all empty sites to the right. Okay, and then we just saw the movie. The thing looks like a fluctuating thing over a parabola. Okay, so the blue is the actual height function, and we're interested in calculating this distribution. And the other special case is flat. Now flat, you wonder how do you make flat? Well, flat is just particle, no particle, particle, no particle, particle, no particle, so it looks like this little wiggly line, but luckily we're far enough away that we don't see that, we just see a flat line. And then the thing just goes, and on top of that there's this fluctuating process. Okay. So now, in these two cases, you study the limit of this, and you discover to your amazement that in this case, the one-dimensional fluctuation at one site is the Tracy-Whittem GUE distribution, and in this case, it's the Tracy-Whittem GOE distribution. So let me just give you a quick primer on random matrix so you know what those are. So just recall that there's these two classic matrix ensembles. So a random matrix means nothing but a n by n matrix with random entries, and usually this is called n. Sorry. Okay, so there's two special ensembles I want to talk about. One is the Gaussian unitary ensemble, and one is the Gaussian orthogonal ensemble. And ensemble just means what's the joint distribution of all these entries. And the joint distributions in those two cases are, well, one of them is supposed to be a complex Hermitian matrix, and one of them is supposed to be a real symmetric matrix. So that means your freedom is just on the diagonal and above, because the ones on the flipped are forced on you. And for those, you just put in IID Gaussians. In this case, complex IID Gaussians, and in this case, real IID Gaussians. Okay, and their mean 0 and variance 1. Okay. So then now you look at the eigenvalues. So these things both have real eigenvalues, n of them, and they basically, when you draw a picture, they look like this. They're spaced between -2 root n and 2 root n. They're sort of denser in the middle, and we're interested in the edges. Okay, so we're interested in what the top eigenvalue looks like, and if you multiply it by root n, you discover that it's 2n plus n to the 1/3 times some special distribution, which is a distribution which depends on what your ensemble is. And in the two cases, it's the GUE Tracy-Whittem distribution or the GOE Tracy distribution. And if you notice, I multiplied by root n just to make the analogy with the interface growth. N is like t. And here you see some constant times t plus t to the 1/3 times non-trivial fluctuations. Okay. Now what about these Tracy-Whittem distributions? They're given by some formulas. The formulas are a result of some huge calculation. For both of them, there's two ways to write the formulas. One way is to write the distribution function as e to the minus what is basically the second integral of a function called q squared. Okay, so all this integrations is just to write two antiderivatives of q squared, where q is the solution of some nonlinear ODE, a famous one called Painlevé 2. Okay? So that's one recipe for the GUE Tracy-Whittem distribution. Another recipe for the GUE Tracy-Whittem distribution is you can write it as the determinant of I minus a special operator, which is defined through its integral kernel, which is this, where AI is the Airy function. And if you don't know what the Airy function is, it's this function. Okay, so now you know what the Airy function is. Okay. Sorry?
There is no S in this second formula.
Oh, yeah. Okay. On L2 of S to infinity. Okay? It's going to come more clear later. Okay. And in GOE, you have something very similar. Okay, well, there's a formula sort of the same, except there's a square root of this FGUE, and there's this Q instead of Q squared. I don't know why. One integral. Or it's the determinant of another kernel. I won't even write that kernel. Okay. So you get the idea. These things have some formulas. The formula are not exactly intuitive. And I would say it's 30 years, and I don't think so far anyone can tell you why. There's no why. All the successes in random matrix theory are, well, we have another ensemble and we can prove that it converges to the same thing. But they're not going to tell you why it converged. There's no story, like the earlier story I showed you with renormalization. You can't say this is the fixed point of some renormalization operation. There's nothing like that. All it is here's a case you can calculate, and here's another case where I can show it's close to that. Okay? And this is the answer after a long calculation. All right. And then there's the second question of why? Why when you start with a wedge do you get GUE, and when you start with flat you get GOE? Why? Okay, and these are real things. So here's a physical realization of the Eden model. This is a liquid crystal. It's about 1 centimeter across. And what Takeuchi in Japan does is he fires a laser beam into the center. The liquid crystal exists in two states, as you know perfectly well by looking at your watch, a dark state and a light state. And he fires a laser beam and the dark state starts invading the light state. And because this thing can be repeated over and over and over and over, he can really measure the fluctuation of the boundary. Okay, and then he gets a lens, and he fires the laser beam through a lens to make a line, and it grows like that. And then he measures the fluctuation of that boundary, and he checks. And yeah, indeed, they match. Okay, this is good matching of 4 moments to the GOE and the GUE, Tracy-Whittem distribution. So anyway, this is something you really see in nature. And it's supposed to be very, very ubiquitous. This is a random Riemannian metric. And you're looking at the balls of radius 1, 2, 3, 4, 5. And the fluctuations of that, I'm just trying to inspire. Somebody in this room should try to, the boundary, the fluctuation there should really be GUE Tracy-Whittem distribution. Okay, so after all that intro, we're left with 2 big questions. What is the KPZ fixed point? And the other big question is universality. How would we show that all these different models converge to this fixed point once we know what it is? The second problem is completely open. I don't know any non-trivial example. And the first one is solved by us. So this is with Konstantin Matetsky and Daniel Remenek. So we were able to solve TASEP, and then you can just pass the limit, and then you get a formula for the KPZ fixed point. So I'm going to show you these formulas. I'm not going to show you the TASEP formula, because the TASEP formula is really just the same as the fixed point formula, but it's nasty because all derivatives are being replaced by discrete derivatives. So it's very, very finicky to write down. But you can just imagine that it's basically the same as the limiting formula. Okay. Just before I do that, I want to give you a little bit of history so you understand where this is coming from. TASEP has been around for a very long time. It was introduced in the late 60s as a model of biopolymers. And from the 70s on, it became essentially the most popular model in non-equilibrium statistical mechanics, partly because it's partly solvable. Well, it turns out to be completely solvable. We're not the first people to solve TASEP. TASEP was solved in 1997 by Schutz, by Günther Schutz, by beta ansatz. Now, beta ansatz is a physics method, but this is a completely rigorous proof. And what he was able to do is think of remember the particles in TASEP. So if you have n particles and you start them somewhere, you can ask, where are they at some time t later? And he can give you a formula for that transition probability. There's the formula. So this is Schutz's formula for the probability that n particles starting at xi's is at yj's at time t. So it's a determinant, it's an n by n determinant with some functions in it, and the functions are defined by some contour integrals. And well, if you're looking at this formula and say, I don't want to think of a formula like this, you will look at it for several years and still have the same impression. It's not a very simple formula, but it's a formula. Now, the problem with a formula like this, so this is n particles to n particles, and there's n particles, there's 5 particles, but now we want to look from a long way off, and you start looking farther and farther. Okay, you guys get the idea. If you have 5 particles, you look from a long way, there were no 5 particles. It's as if you had 0 particles. So the problem is you have to somehow get the large n limit of the Schutz's formula. But the Schutz's formula is not set up in a way to get a large n limit, except in very, very special situations. So in the wedge situation, it turns out that the Schutz's formula is essentially has a Toeplitz structure. And a Toeplitz matrix, people know how to take the large n limit of a Toeplitz matrix. So that's why only very special initial data. Now, Sasimoto really should be credited with the huge advance on TASEP. Sasimoto looked at Schutz's formula and realized that Schutz's formula had an amazing structure. The F's satisfy a certain recursion, which when you try to simplify the determinant, you realize what this thing is telling you is it can be written as a determinantal point process over a space of what's called Gelfand-Zeitlin patterns. I'm not going to go into it because it would take, I don't think it can be explained in less than half an hour. I'll say it once more. The special structure of Schutz's formula, here, the Fn satisfy a recursion, which mean that when you try to reduce the determinant, it ends up being a determinantal point process on the space of Gelfand-Zeitlin patterns. It's not a normal determinantal point process. It's not even a probability measure. It's a signed determinantal point process. But nevertheless, there's a machinery called Einard-Meda, which tells that if you have a determinantal point process, you can calculate the top line of the determinantal point process as a determinant of a certain matrix, which is the inverse of the correlation kernel. Okay, so that's a long story in a short paragraph. I'm going to tell you the result of all that and where things stood in 2005 after Sasimoto's idea. Here's the problem. This is the biorthogonalization problem for TASEP. So by 2005, they knew that you could solve TASEP, and solve TASEP, maybe you should look at the bottom. Solve TASEP means you can, starting from any initial data, you can calculate the finite dimensional distribution at time t later as a determinant of a certain kernel, which can be constructed through a recipe, which I won't explain the whole recipe, but I'll show you the hard part of the recipe. The hard part of the recipe is that this k can be constructed out of the sum of phi's and psi's, and the phi's and psi's come from the problem above. So let's read the problem above. Okay. The problem above is a well-contained mathematical problem. You have Charlier polynomials. Charlier polynomials are orthogonal polynomials on z plus with respect to the Poisson measure. If you don't like that, there's some funny hypergeometric functions. If you don't like it, think in your mind, we have Hermite polynomials, and they're orthogonal polynomials with respect to the Gaussian measure. Okay? You won't be far off because there's a model like TASEP, which is a little bit hard to describe, for which the problem becomes exactly that problem with the Hermites instead of Charliers. Okay. So you've got these Charlier polynomials, and they're orthogonal with respect to the Poisson measure. And now you take your particles. So your particles have some initial positions. And it's very important here that there's a last particle to the right. But in a sense, that doesn't matter because we can put it as far off to the right as we like, so it doesn't matter. Okay, so we have initial particles at these positions. They're ordered in the wrong way, and history gave me that, I'm sorry. Okay, so they're ordered backwards from the rightmost. 1, 2, 3, 4, 5. Okay. Now you take those particles and you shift them by their name, by their number, and you call that x hat. Okay? And now you take these orthogonal polynomials ck, and with the measure, so you take this whole piece and you shift it by x0 hat. Okay? So you have orthogonal polynomials, and now you shift them by the initial data. And then the problem is to find new polynomials which are biorthogonal to the ones you've got by shifting. That's the biorthogonalization problem for TASAP. Once you have those new polynomials, the phi's, then you can build this k, and then there's a simple recipe to produce this guy, and then you've got your transition probabilities. Now, the only problem is, what are the phi's? Now you might think, oh, I know how to solve this problem. I got to guess. The phi's are just going to be the c shifted by the x hats. So, of course, they'll still be, if you take the same one, you'll still get a 1, but they won't be orthogonal anymore. And then you start thinking, what's my second guess? Does anybody have a second guess? So what happens is that if you start with wedge or flat, the first guess works. Anything else, the first guess doesn't work. And nobody has a second guess. So things stood for 12 years, and we discovered what they are. Phi k's are basically up to a simple matrix. The probability that a geometric random walk first hits the epigraph of the x zeros at time k. The epigraph just means above. It's going to come in a second, so you need to know it now. Epigraph of a function is all the stuff above a function. The hypergraph is all the stuff below. Okay. It's a formula. It works. It's not that hard to check. It always works. There's no conditions in the theorem. Okay, so you got the phi's. You got the phi's, then you construct the k, which means you've solved TASAP completely. You got a formula, and it's a workable formula. And now you take a limit, this 1, 2, 3 scaling limit, and you have a formula for the fixed point. So let me show you this formula. Okay, so here's the formula for the KPZ fixed point. So, of course, the formula has the same structure as you saw before. I set it up like that. So you start with your initial h0, and now you want to know your finite dimensional distributions at some time t later. They're given by a determinant of an operator, which is defined in the following way. So now you see the t is now inside the k. Okay? And you'll see how it comes. Okay. So this k has this simple evolution, a trivial linear evolution of a base k, which is computed from your initial data. So from your initial data, you compute an operator called kh0. It's the Brownian scattering transform of h0. And then you have this simple evolution. These are the derivative operators. So you solve this PD, if you like. You get this k, and that determinant gives you your transition probability. So all I have to explain to you is how you get from h0 to this kh0. Okay. So here's h0, the red line. You ask the following question. You ask, suppose that I had a Brownian bridge from u1 at minus L to u2 at L, and you ask, what's the probability that that Brownian bridge entered the hypergraph of h0? There it is. It entered the hypergraph. Call that P hit H0 from minus L to L. It's a function of U1 and U2, and I want to think of it as the kernel of an operator. Okay? You could ask a question. You could say, suppose I know P hit from minus L to L. Do I know H0 from minus L to L? Of course, you don't know it outside, obviously. But do you know H0? It's not obvious. Turns out you do. Turns out it's true. So it's actually a one-to-one mapping between H0 and KH0 from minus L to L. Okay? But we need H0 on the whole line. So what we do is you try to take a limit of hit. But one thing is clear. If you try to take a limit, then this property that you actually know the function would go away because the Brownian motion is too blurry in the middle. So what it tells you to do is you refocus on the middle by solving the heat equation backwards on both sides. Okay? Now you could wonder, oh, and then you take a limit. And I claim the limit exists. And this is the Brownian scattering transform of H0. And I claim you can compute it in special cases. So for example, in a case like flat, you can compute this thing. You just use the reflection principle, right? And lo and behold, K of flat is the reflection operator. Narrow wedge, you can compute it too. So you can compute it in all the cases which were known. And then there's this thing about this backwards heat equation, and I know your mother told you not to try to solve the heat equation backwards, but it's okay. It's okay because this guy here is so regularizing that as long as T is positive, it allows you to solve heat equations backwards and forwards. That's because this operator, e to the td cubed plus xd squared, it's just a beautiful operator for any x. X equals minus 10, I don't care. You can solve the heat equation backwards as long as you have this area operator in front. This thing is just given by this kernel. It has a kernel, so it's actually a group. As long as t is not equal to 0, it's actually a group in X. Okay. So that's the KPZ fixed point formula. And if you indulge me 2 more minutes. This formula is screaming at you to do something, which is to differentiate the determinant. It's actually screaming at you to differentiate the log of the determinant because of all these derivatives up here. So we did so, and we discovered the following amazing thing. Oh, sorry. This is just a picture of the complete integrability of the KPZ fixed point. So of course this tells you that these things are all integrable systems, TASAP and the KPZ fixed point, and here's just the description of what I just said. But okay. From the form of the kernel, differentiating, we were able to discover the following very surprising thing. You take the 1D marginals of the KPZ fixed point. So those are the universal 1D marginals of one-dimensional random growth. So you've got a time and an x and a r, which is your variable in your distribution function. So it's a function of 3 variables. And you take the log derivative, well, the second log derivative, call it phi. It satisfies this famous equation Kp, the 2-dimensional KdV equation. Just stare at that for a second. It's not something anybody expected. The most amazing thing, perhaps, is that it satisfies an equation. Why on earth would the 1D marginals of something like this satisfy a closed equation? The next and most amazing thing is, Why KdV? Where did KdV, the Korteweg de Vries equation, come from? But the thing has consequences. Tracy-Whittem GOE and GUE distribution. Now you know what they are. They're just special self-similar solutions of KP. Well, in the GOE case, it's flat, so there's no x dependence at all. If there's no x dependence, this term drops out, and this is just the Korteweg de Vries equation. The Tracy-Whittem GOE distribution is nothing but the similarity solution of KdV at a fixed time. GUE is just the similarity solution of KP. Okay. So that's the universal equation. After all that, its scaling invariant is certainly not what we expected. So just to wrap up, we started with general models, and we found there's a special model for which we could get exact solutions. And from the exact solutions, we got our physical law, which is not usually how mathematical physics goes.
So you said at the end that these Tracy-Whittem distributions, you could see them as special solutions to this equation. Do you have any idea, like, why, we first know them as equations of random matrix theory. Do you have any idea from this perspective why they would be, what they are in random matrix theory?
Okay, so the question I have to repeat, I hope I repeat it right, is now if you want to go back to random matrix theory, what the heck does random matrix theory have to do with this? Does this help in random matrix theory? Well, the problem is you don't have as many initial distributions. But if you're a random matrix person, and you want to see this say GOE as the self-similar solution of KdV, then when you scale out n, just add a t. This is, I claim, my big contribution to the subject is to add the t. So you put nt instead of n, and look at it as a function of t as well, and it will satisfy KdV. You can check. Of course, I don't know how much that helps. and GUE too, with the KP. Yeah. Yeah.
I don't know. I mean, these equations are completely integrable.
Right. So.
There is a relation between the.
Okay. So this question is about the complete integrability of KP and what it has to do with this. So, complete integrability. Although I showed you a different kind of slide, in reality, what they mean by complete integrability is I can give you a formula for lots of solutions. Okay? Now, the initial data which I have for my KP is not in their world. On the other hand, I can give you a formula for lots of solutions. So I already proved that KP with my type of initial data is completely integrable. That's actually what it means. But I went backwards. I used the completely integrable solution to get the equation. So it's a bit weird. Yeah.
What are their AI? AI function or what?
AI just means the Airy function. That guy. Yeah. Any other questions? Yes. Yeah, where's the dependence on H0 in the KP? It's a very good question. I didn't write it, and I would be happy to show you after, but it would take a few minutes. You see, if you look at that f, it's not too hard to figure out what f is for time 0, because it's just a deterministic function, h0 less than r, Actually, that's the answer. That's all I would tell you after.
Is there any other cases of H0 other than flatline and wedge that lead to some sort of simple solution?
Are there any other special? Yeah. So there's a couple of other cases where it's not as self-similar, but they give you, it reduces the equation down by 1 dimension or something like that, and you get some PDE. I don't know any other where you actually reduce the thing to an ODE like Panleve 2. It's a very good question. We've been looking for it, of course. I don't believe the beta ensembles are here.
Do you know the physical content of cadence between equation?
So the question was, do you know the physical content of the KP equation? The answer is, in this case, 0. There's absolutely no physical understanding of why KP comes up in this case. 0. Of course I'm trying.